first talk of this workshop, which I missed, and I've heard that some of you also missed. I will repeat a little bit, like tiny bit about that talk, and also I will go on and talk about these new results, which is about short depth designs, or the possibility of short depth designs for groups other than the unitary group, but which are subgroups of the unitary group. Yeah, I mean, and this is of course actually it's a work done by together with many people here. The reason for this this amount of people was that actually this came in a conference. These ideas came up at the conference where we were discussing random circuits, and then there was this collective input which resulted these results that I'm going to talk about. So we are talking about approximate unitary designs, and then later on other designs for other groups, so unitary K designs. I mean, we all know here, I guess, the definitions, but what it roughly means is that that we have an observer, and we have it's given randomly selected k-fold tensor products of unitaries, either randomly selected from a high randomness or in some other ways, and then if with all types of experiments that he can do, it's all the results are close to what he would get from the hard random case, then we would call it a design. That's another way of stating what you all know, the definitions. And of course, one of the the best way of getting high K designs, it has been thought, is that to do, let's say, a brickwork circuit of, let's say, 2 qubit or 3 qubit gates, and it was like often asked, this question was asked, like how fast would it converge to a approximate K design? And like there was this seminal work by Brandao, Haro, and Orodetsky, and after that there were many follow-ups that made that work, improved that work in various ways, but it was always of the form that actually you would have at least like n times k and times maybe polylog k, this type of depth was needed. And it was also thought that that it is impossible to have, for example, in n sublinear scaling system size. And the reason for that was that, well, one could show with a simple light-cone argument that it would produce much less entanglement than, say, a random unitary circuit would produce. But entanglement is, of course, very hard to observe in some sense. Like so. So basically, that was not like really a valid argument. And then came this gluing lemma, which was presented in the first talk. And what did this mean? Basically, what you could do here is that it turned out that actually with if you do a small unitary design here and do a very small overlap with another unitary design, actually it's a unitary design over the full ones, and then you could make this argument that you could actually glue these shorter unitary designs together to a bigger unitary designs, and then the depth was in log n. Okay, and a natural question to ask, what happens with other groups? I mean, one possibility is that if we go back to this brickwork picture, we could do a very simple change. Let's say we take Q-trit gates, but the Q-trit gates should all be from the unitary symplectic group. And And then we do this brickwork circuit with, sorry, not QD, but 3 QD gates, let's say, like 3-fold QD gates, and from the unitary symplectic group. And then what you would do is that you would ask this question there. And you could ask an even more, why I'm meaning the unitary symplectic group and not other group, is that you can actually make that question a little bit even interesting, because we know that if it would take a pure state here, and we would evolve that pure state with a hard random unitary and a hard random unitary symplectic gate, you would get the same distribution. I mean, this follows basically from the fact that on pure state, the unitary symplectic group acts transitively. So, I mean, what would be a more natural idea? Like, would it be, if it has that power, this unitary symplectic group, wouldn't we believe that basically we could get, we would have the same result here as for the unitary group? Or we could ask another very similar question, like do the same setup as for the unitary group, but for real states and orthogonal operations that acts transitively over the real pure states, and what would happen there. And at first, surprising thing will be that everything will be different, although probably you heard about that in the first talk. And the main reason for this, from my point of view, is that there are higher order conserved quantities that can be basically written as a tensor product over the space of qubits. So what do I mean by that? So basically, what we have is that if we take any subgroup of the unitary group, we know that at most in the k-fold tensor product representation, you will have quantities in the commutant that doesn't appear in the commutant of the unitary group k-fold tensor representation. I mean, k-fold tensor of the defining representation. But interestingly, for the cases that we will study, and these are the most studied cases, these elements, which are often appear in the second tensor power for connected compact groups, there will always be like that. And for the Clifford group, it will be in the fourth power. These quantities will actually be such that they factorize in the qubit dimension. So these basically, what you can imagine is that you have you take the SO2 to the n group. We know that, for example, in SOD in general, you have that you will have there will be a sort of generalized Bell state in the second order commutant, which is left invariant by the O tensor O operations. But such a state, if you take D to be 2 to the n, like so we have qubits, it actually factorizes as tensor products of Bell states over 2 qubit spaces, where this is like the design direction. And this is always what we will have in what we will talk about, that in the commutant we will have a new chi, which factorizes in the qubit dimension and is entangling, only in the design direction. And we can actually choose it to be positive semi-definite, and it's not the identity. And that's actually important, but a little bit of a triviality. And then we can do the trick that I will show. And this is all the trick that we did for proving the lower bounds of the groups that we did. But we, of course, had to adapt to the different groups. So basically what we will do is that we will take that chi operator, and And then instead of that chi operator, we will take a Q where chi is multiplied from the left and right with Z tensor identity on all the other design components, Z tensor identity on all the components. And then if we take U tensor K, U dagger tensor K, so this operation, then it turns out that, of course, if you write here U dagger, then that commutes over what is rest over chi. So actually what you will get is that you will get this U Z1 U dagger operator here, U Z1 U dagger operator here, and tensor identities here, and the chi. We call this the light cone smuggling. And how would this look like, this U Z1 U dagger? Well, basically, you would connect such a circuit. So everything here, if this was U and this was U dagger, everything here would cancel, and you would have basically here the identities, and what you will have here, the operator that it will give you has this structure that it's only supported on these qubits. And then if we put this into the full picture, what we will have is that this operator U tensor KQ U dagger tensor K has to look like that there is some operator here, but after a while, after the depth of this, you have these chi's. And basically, this is very different in depth D from the case what you would have from a random circuit. The random would totally scramble the components of Z all over. And using this trick, we can have a look a little bit. We were able to get some lower bounds on when the Clifford orthogonal symplectic group and the matchgate designs how big depth they need. And basically, for the 1D architecture for this linear connectivity, you would at least have a linear depth instead of the logarithmic one. For the unitary designs, for the 2D architecture, you would have a square root of n, and for the all-to-all, actually you would have a lower bound, which gives you log n, while the all-to-all have their log n. So this can be a little bit made in parallel with the case of symmetric circuits, I would say. So symmetric circuit would be a circuit where you would have a conserved quantity. So you have a conserved quantity which is, let's say, a tensor product of operators. If this would be like a tensor product of positive operators, this what generates it, or there would be a local conserved quantity. That's another one, like invariant circuit. You could play the same game. What we did here was actually to elevate this to the level of groups that will have these quantities, but in the tensor product representation. So if you take this, they're defining representation, but to the tensor product of 2 or k-fold. Okay, so yes. So before I make that comment, so this was about like this type of operations can be shown using this. We could show that there is no you have this linear lower bound for generating orthogonal or symplectic or Clifford designs with local orthogonal symplectic Clifford gates, let's say in a linear nearest neighbor topology. However, the question arises: what about the state design? So what if I'm interested in just the state? And then, of course, for the states, you have two cases, two types of measures how we would define whether you are close enough. One is the relative error design. The other one is the additive error design. And it turns out that this argument, this previous argument with the light cones, can be just carried over and shown that that the relative designs will also need such deep circuits. Interestingly, that's a funny part, actually for the additive error, the state designs for some of the groups can be made actually with short circuits. In particular, we have to a little bit talk about what we mean by state designs, because of course for the unitary group it doesn't matter almost or which state you start with, but here it will matter. So for example, if we start from the symplectic group or from the orthogonal group, if we start with a state which has a low entanglement, or to be more precise, we start from a state which is a positive partial transpose state, then basically we could show that that if we would apply our symplectic or orthogonal design, you would get the same thing as the unitary design with an additive, very small additive error. And then what we did was to show that actually also what will happen is that after applying our designs to a PPT state, we get PPT states, and we could do the same type of division trick here, and the G designs would also be in additive error close to these type of unitary designs. And since the unitary designs have this gluing property, also for the G designs we will have the gluing property. That was like the main idea how we proved it. So this was not true for all the groups though, but only as you can see, for the orthogonal, the unitary symplectic and the Clifford group, where we got this gluing lemma, so we could say that it glued there. But for the free fermions or matchgates, we did not have this type of gluing lemma even for this PPT state, which is an interesting fact. So in the end, what we got, that actually what Jonas was telling, that for the unitary symplectic group you have this gluing for the relative and additive group designs, for the relative state designs, additive state designs, and for the anti-concentration you can use this. For these other groups you have this interesting web. What I put here is what we have proved, and there are a lot of open questions that we are working on now which are still there. So for example, we showed that in the orthogonal and in the symplectic case, in the Clifford case, we have the linear lower bound. Then you could ask whether is this a tight lower bound? So is it really that after linear depth, if you put random Clifford or random orthogonal gates, whether do you get really a design? And obviously, I think people who have been studying, let's say, fermionic linear optics or bosonic linear optics has a guess already, and the guess is no. And actually my guess is no for all those groups. Basically what you will have is that you will have a diffusion type of process, and you will have to do if you want an n squared depth, if you have n number of qubits, n squared depth will give you a good scrambling of the conserved quantity, I would say. Okay, but then you could also ask, and this question is of course loaded, you could see that maybe we are already, or some of us are working on this from the previous group. So, okay, so there are these degrees of freedom which are related to these sort of conserved quantities. But what about the other degrees of freedom? For them, for the other than the k-fold symmetry, so other observables, is there a gluing lemma? You could ask. Probably the answer will be yes. And then also connected to this with the degrees of freedom, you can also ask a more generic group theory question, which is like, we know that in some cases, for example, the Clifford case, if you have you have extra symmetries in the fourth tensor copy, but they don't generate then all the symmetries. For example, you need, I think, in the sixfold tensor copies, and those two generate. But of course, those the cases when you have a connected compact Lie group, and the Lie algebra that totally controls the behavior, then usually what happens in many of those cases is that actually that Lie group can be characterized with the twofold symmetries. For example, the orthogonal group, you can characterize exactly those elements that commute with that twofold symmetry, the unitary symplectic as well. And then for those, is it true that all the twofold symmetry generate the k-fold symmetries? And actually my feeling is yes, and that could have actually, that could ease up this proof, this other than other than k-fold symmetric symmetries, whether they glue or they thermalize that question. And then, okay, so then there is an interesting question that we observe this discrepancy for the additive error state designs between the orthogonal symplectic versus the match gates. And then this is worth to explore. And also it's worth to ask what happens when we have actually symmetries on the physical layer already, not in the k-fold tensor product. What happens there? And right, I mean, I think what will happen there is that this discrepancy will be on the level whether you have a local conserved quantity or just a global quantity that is which commutes with everything, like whether you have particle number degrees of particle number symmetry, that would be sort of the match gate case. If you would have parity symmetric, that would be the orthogonal, the symplectic case actually. And in one case you would have a short design on state design on in this relative additive error. In the other you wouldn't. And finally, another question which actually many people have worked on here, so I should mention there is a nice paper here, many of the authors are here, on doping Clifford circuits. Of course, what you could do is that we know that actually if you have a Clifford circuit, to get a good K design, you don't need to put in too many T gates, but for that you have to put these big Clifford operators in. So then the question is, okay, so then it means that, okay, still because we cannot remove these big Cliffords from there because we cannot remove it and make them shallow, probably. From the, it doesn't exactly follow, but it's a hint that you cannot do it from this, from these ideas that we have done here. Okay, so what then? I mean, what you can do is that, you know, of course, if you have then many T gates, so you have two qubit Cliffords and then T gates, so after the two qubit Cliffords and something like that, then that's basically like a description of unitaries, and in a short, you can do a short design there, like a logarithmic depth design, which like that. So one would be then at least like a deep design, the other would be short. So okay, so we understand those big, these extremes, but what should we? How can we tune it? So basically, if we would start to dope more and more, probably we can remove this, that you have to do an arbitrary Clifford. You can put shorter and shorter Cliffords there, and then the question remains: so what type of transitions would you have that, and when does it happen, and how does it happen, or is it something smooth? Okay, basically, thanks a lot. These were all the outlooks.
Okay, so we have a bit of time for some questions. Thanks, Zoltan, for a great talk. I have a question about your first open problem about matching upper bounds. I'm actually confused for the special case of like bosonic or fermionic
Yes.
linear optics, because then you can compile just high random, say, matchgate circuit in linear depth, and you mentioned
Yes.
quadratic depth.
Yes, yes, but if you would do the following thing, so what I mean by this, I tell you what I mean by this. That's of course true, that you would take 2 Q-mode or 2 qubit random gates from the respective linear optics of linear fermionics gates and put them completely IID after each other. After linear depth, they would not become a good design. Only after quadratic depth. Of course, you could then compile it back. That's true.
Okay,
that's true.
Thanks. So you can like maybe deform. Maybe like the hope would be that's like
by
deforming those like random.
You can deform, but let me tell you something that it has connection to other areas of, for example, if you want to do, let's say, generative learning, we do this with fermion sampling now. Actually, we enter this problem that if they want to learn with the usual parameters, like the one how you would do the decomposition into a linear gate, which could give you anything, they are not able to learn, my students were not able to learn certain probability distributions. But just by adding layers and layers and layers and layers, so over-parameterizing, which you can then actually make shallower then, back to linear depth, they were able to learn. So this has also consequences. Like you can deform it, but this deformation is like a little bit weird.
Thanks.
Is there some?
Thank you for the very nice talk. This could be a very naive question. It seems like a lot of the lower bounds are coming from these unitary light cone arguments.
Exactly. Well, yes, light cone type of arguments, yes.
And recently, I know people have thought about using like measurement and feedback to deterministically prepare, say, like long-range topological states. And these kind of violate, say, like Lee Robinson light cone type arguments. But is there any chance that that kind of ingredient could be helpful as a tool in constructing these designs, or?
Yes, I mean, you mean that also you have to add ancillas.
Right, right. Things like
if you add ancillas, everything changes.
Okay.
Also, everything changes with the unitary designs, yeah.
Then you can do it in constant depth.
Right, right.
With measurements, it's known that you can do it.
I see. I see. Very good. Thank you.
Okay. So if there are no more questions, let's thank the speaker again.
Thanks.